So we're ready to move now to the next speaker, who is Michael Hammer from the University of Arizona. And he's giving a dissertation talk titled The Effects of Realistic Planet Formation in Timescales on Planet-Induced Vortices. So Michael, you have 15 minutes for your presentation. I will give you a 2-minute warning.
Okay, great, thanks. So hello everyone, and welcome to my dissertation talk. I'm so excited. I've been looking forward to this ever since my first AAS meeting as an undergrad, and it's finally here. So during my PhD, I've studied vortices in proplanetary disks, and this talk would not be possible without my collaborators, Caitlin Crowder, Paola Pinilla, and Minkai Lin, and of course, the actual vortices in proplanetary disks. But are there actually vortices in proplanetary disks? We think the answer to that is yes. In the past decade, ALMA has observed several crescent-shaped features in various proplanetary disks. For a few of these, including HD 135344b, which is this one right here, we have observations of the same crescent at different wavelengths. If we look at the azimuthal extents of these crescents, then the larger wavelength shows that the larger grains are more concentrated. Meanwhile, the smaller wavelength shows that the smaller grains that would be harder to trap at the center of a vortex are much more spread out. Now that's the type of behavior that we would expect to see in a vortex. But how do these vortices form to begin with? Well, one of the most favorable ideas is that they were generated by gap opening planets. Now we can watch this happen by running hydrodynamic simulations of a gap opening planet in a disk of gas. Now most previous studies of this problem start with a gas distribution following this smooth radial density profile. They then add a Jupiter mass planet to the disk, and after running the simulation, they find that the planet will quickly open up a gap within about 100 orbits, which creates a sharp peak in the disk's radial density profile. Now, if that peak is too steep, it will make the disk unstable and trigger the Rossby wave instability, which will eventually create a vortex. Now let's watch what that looks like. So in this simulation, the planet grows to Jupiter mass in just 10 orbits. Soon after, the disk becomes unstable, forming several smaller vortices. Then, these vortices will merge into one big vortex in less than 100 orbits. So now, the vortex has a width of about 120 degrees, and its maximum density is more than twice the initial density at the location of the planet. Now, if we continue the video, we'll see that the vortex lasts about 7,500 orbits, which is more than 500,000 years if the planet is at 20 AU. Now, if we compare the gas surface density to ALMA observations, we'll see that they match up pretty well. But we shouldn't do that because ALMA probes the dust, not the gas. If we compare the dust to the observations, then you'll notice that the dust is much more concentrated than the gas. In fact, it's so concentrated near the center that if you were to observe the disk from the simulation with a similar beam size, then you'll see that the vortex no longer looks like the crescent on the left. Instead, it's just a small blob. So, can we reconcile simulations of vortices with the observations taken by ALMA? Well, we weren't surprised when we saw those ALMA images because we already knew that placing a fully grown Jupiter mass planet in a disk instantly isn't actually a good idea. So let's take a look at what happens when we place the planet in the disk more slowly. So for this simulation, we use the same parameters as the previous video, except that now we prescribe the planet to grow to full size over 1,000 orbits instead of just 10. Now, in this case, when the planet reaches a fifth of a Jupiter mass at about 300 orbits, it makes the disk unstable and triggers a vortex. Though this time the vortex is a lot weaker than before. It never reached as high of a density, and its width is about 240 degrees, which is twice as large as in the other case. And then even worse, the vortex only lasts about 1,500 orbits, which is 5 times less than when the planet was placed in the disk almost instantly. So there are 2 types of vortices. If the planet grows instantly, you form a compact vortex that's well described by the relatively new Gaussian model. And if the planet grows slowly, you form an elongated vortex that's well described by the classic GNG model. Now recently, Serval and Barge studied both types of vortices, and they found that the difference between the elongated and the compact models wasn't actually so much the extent of the vortex, but really the minimum Rossby number in the vortex, which is just the amount of vorticity in the vortex. So if the minimum was less than minus 0.15, then the vortex would be compact. And if it's more than minus 0.15, so if it's less negative, then the vortex would be elongated. Now it's relatively easy to see why a slowly growing planet produces a weaker vortex. When the planet grows slowly, the initial set of vortices that form instead have elongated Rossby numbers that are greater than minus 0.15. Now when these vortices merge, the final vortex also has an elongated Rossby number. And even worse, it never develops a clear vorticity minimum at its center. As a result, when the planet continues to grow, it can't strengthen the vortex or cause the Rossby number to drop as much as it does when the planet grows instantly. Now, why do these vortices form to begin with? Well, normally, if you have a denser fluid on top of a less dense fluid, then that would be unstable. And that's exactly what we have here, where the outer gap edge is much denser than the actual gap. Now, in this case, though, the fact that the disk is rotating stabilizes the gap and prevents the pileup of material at the gap edge from just sinking toward the star. Now, but that rotation also allows Rossby waves to form on both sides of the gap edge. Now there's one over here moving in this direction, and then there's another on the other side of the gap edge that moves in the opposite direction. Now that would be fine. And then these waves also have a few peaks that also move in opposite directions. Now that would be fine, except that these waves are fairly close together. And then even worse, Rossby waves are transverse, which means that the peaks extend laterally. So if you're in the middle, the blue wave is telling you to move forward, and then the red wave is telling you to move back. And then the blue wave tells you to move forward, and so on until you swirl up and form a vortex. And you end up forming one vortex at each peak. Now these elongated vortices look a lot more like the ALMA image that I showed before in the gas. But what about the dust? Now as it turns out, elongated vortices still trap dust, but not in the center of the vortex. So just like with normal vortices, the increase in density at the edge of the vortex creates a pressure bump that, when combined with the rotating velocity field of the vortex, naturally traps dust. However, that's where the similarities end. If I add contours to both vortices, then you'll see that the compact vortex has nice elliptical contours and a very smooth pressure bump, while the elongated vortex does not. As a result, once the vortex collects dust, that dust has no reason to spiral inward to the center like it does in a normal vortex. So what happens instead? Instead, the dust circulates around the vortex, as you can see here, for 1 centimeter and 3 millimeter size grains. Now this motion leaves the vortex nearly as elongated in the dust as it is in the gas. And furthermore, it also leaves the peak in the dust density off-center most of the time, which creates a big distinction between concentrated and elongated vortices. Now with the dust circulating, do elongated vortices actually look elongated? The answer is yes, some of the time, but not necessarily. Now, as the dust circulates through the middle of the vortex, it does typically appear elongated. But when the peak reaches the edges, then it can also look more compact. So with both outcomes possible, it's not straightforward to infer the extent of the gas vortex just from looking at the dust. So going back to the beginning of the talk, we couldn't explain this Alma image too well with a compact vortex, but an elongated vortex does a much better job. Now let's move on to what can kill the vortex. Now in the second movie I showed, the elongated vortex dies out by eventually spreading into a ring. But why did that happen? Well, viscosity is one way to kill a vortex, but you need an alpha of at least 10 to the minus 4 for that to happen quickly. And the movies I've shown so far don't actually have that high of a viscosity. Now, instead, the elongated vortex I showed at the beginning actually died because of shocks from the planet's spiral waves. But that doesn't always happen. Now, if we increase the H over R to a very high 0.08, the vortex hardly changes after it forms. Now you can see it does decay, but that happens very, very slowly. And the vortex survives for thousands of orbits because the shocks from the planet's spiral waves are too weak to dissipate it. As a result, the vortex never spreads into a ring, and it's still alive at the end of this movie. Now with H over R equals 0.06 though, we already saw at the beginning that shocks can kill the vortex in a little more than 1,000 orbits. But does that always happen? Now as it turns out, the answer is yes, but with lower mass planets, the vortex can actually reform. Now in this simulation, the planet only grows to about 0.2 Jupiter masses. Now, like the other cases, the initial vortex only lasts a little more than 1,000 orbits. But this time the vortex can reform. And in fact, it happens at least 3 times, at about 2,600 orbits, at about 3,100.
Michael, you have 2 minutes left.
Thanks. At 3,150 orbits and 3,660 orbits. And in total, the vortex survives more than 5,000 orbits. And it's still alive at the end of this movie, which gives it a way longer lifetime than the Jupiter mass case. Now, one of the great things about the AAS meeting is that it's set up for undergrads to present, just like I did in 2014. When I presented not one poster, but 2 posters, and I also got to see some of my RIU friends. And then besides that, for no particular reason at all, except that I like planets, I went to this session and this talk where I saw Jane Berkby advertise the LEAPS undergraduate summer research program at Leiden. Now, I'd never heard of it before, and I probably wouldn't have heard of it otherwise. But I ended up deciding to apply, and I got accepted, and so I got to do more research that summer. And And even better, I got to go back to the AAS meeting the following year. Now, also in 2014, one of my goals was to meet Astrobite authors because I love Astrobites. And I was very happy to meet Nathan, who was one of the founders of the site. And now here I am in 2021, not only writing for Astrobites, but also covering the AAS meeting for Astrobites. And I've even gotten a recommendation letter from Nathan himself. So I don't know who's in the audience now, but whoever is here, especially if this is your first conference, be on the lookout for opportunities, both intentional and unintentional, because talking to people and going to talks can go a long way. So to summarize, vortices that are elongated can indicate the associated planet grew slowly. These vortices are often characterized by wide azimuthal extents and off-center peaks, but they can also appear more compact. With H/R less than 0.06, low-mass planets actually generate longer-lived dust asymmetries than Jupiter-mass planets because the vortex can reform. And with a very high H/R, the initial vortex might not die at all because the shocks from the planet that normally kill it are too weak to do so. And if you read our paper, you'll see that both of those effects are due to the planet's spiral waves. So yeah, that was the talk. If you have any questions, feel free to ask or to contact me. Thank you all for attending.
Thank you very much, Michael, for this wonderful talk. Great animations for sharing your journey through the AAS meetings. We have a few questions already. So the first question from Kundan Kadam, fantastic talk, congratulations on the PhD. Is the dust included in the hydrocode at a fixed Stokes number or fixed particle size?
That's a good question. So when I've done my simulations, I've done it with a fixed grain size.
Okay. We have a next question by John Ramsey. Can you say something about the dust density contrast of the former vortices, now rings? For example, how do they compare to what we know from observed protoplanetary disks?
Well, that's also a good question. So because you have drift, because the millimeter size grains above have very high drift speeds, the contrast, the dust contrast in the vortex really just depends on how much dust is available to drift inward into the vortex. So if you had an unlimited supply of centimeter-sized grains, then you can build up a really high contrast very quickly. Now in a real disk, that might not happen because if you're in the outer disk, then the growth times for the grains are much slower, so you might not actually have a lot of very big grains. But the main answer to your question is that it can vary a lot because it's really just dependent on the amount of dust that's available.
Thank you. We have another question from Mordecai McLeod. Nice talk. Care to speculate on how the vortices will behave with vertical stratification of viscosity, for example, due to MHD effects?
Due to vertical, yeah. So my my advisor, Min-Kai Lin, has worked on that, and I think he's shown at least maybe not with an actual MHD simulation, but just with a layered viscosity model that that helps to break up the vortex much quicker. But I'd be curious to know if instead of a layered viscosity, if you just have like a layered accretion model, like with disk wind, would that also break out? Would that also break up the vortex? I haven't investigated that, but hopefully I can do that in the future, maybe even with you.
Thank you, Michael. We have a question, another question by Mordecai. These queen models would be very interesting. Actually, that's a comment. And so I think we are getting some more questions. So let me ask you a question that I thought about. What are some of the aspects from your models that have surprised you, something that you did not expect?
That's a cool question. So when I started this project, this wasn't actually my project. I was actually working on the effect of vortices, or on how the presence of vortices affect planet migration. But then while I was doing that, my advisor, Caitlin, thought it was a good idea to try out like different different growth times for the planet to make sure that wouldn't actually affect the results. And so I did that up to 100 orbits, and then she asked me why I didn't try larger ones, and I said I didn't want to try larger ones because I didn't think the vortex would actually form if you did that. So I was kind of one thing led to another, and then now I ended up with this project for my PhD. So so I would say the project itself surprised me in that sense. And I guess I was surprised actually that vortices could still form at all when you have the longer growth times. And I was surprised that this actually ended up as my project.
Thank you so much, Michael. We don't have any more time for more questions, but there is a few on the Slack channel that you can answer personally. So thank you for your contribution, and we are ready to move on to the next speaker.